Hello everyone, and welcome to the lecture discussing what an adjacency matrix is and what an adjacency list is. So we're going to learn how to represent graphs in this lecture. And as I mentioned, we're going to learn how to represent them as an adjacency matrix and an adjacency list. And in the next lecture, we'll actually implement an adjacency list in Python. So let's discuss what a adjacency matrix is first. It's one of the easiest ways to implement a graph, and we just use a two-dimensional matrix. In the matrix implementation, each of the rows and columns represent a single vertex in the graph. The value that is stored in the cell at that intersection of row V and column W indicates if there's an edge from vertex V to vertex W. And then when the two vertices are connected by an edge, we say that they are adjacent. So for example, here you can see a matrix, or an adjacency matrix, and the value in each of these particular cells represents the weight of an edge from that vertex V to vertex W, so that rows to that columns. So for example, here I have vertex 0 in the row and vertex 1 in the column. The edge that connects them has a weight of 5. And then we can go along and see that V2 and V1 are connected with a weight of 4, etc. So that's how we can actually represent a graph in a matrix form, which is useful to know. So the advantage of the adjacency matrix is that it's simple, and for small graphs, it's really easy to see which nodes are connected to the other nodes. However, notice that most of the cells in that matrix were empty. That's because most of the cells are empty because the matrix is sparse. A matrix is not a very efficient way to store sparse data because you have to store all those empty cells. In fact, in Python, you usually have to go out of your way to even create a matrix structure like the one we just saw. What the adjacency matrix is good for, it's a good implementation for a graph when the numbers of edges is large. But what do we mean by large, and how many edges would be needed to fill that matrix? Since there is one row and one column for every vertex in the graph, the number of edges required to fill the matrix is the magnitude of V squared. And a matrix is full when every vertex is connected to another vertex. There are a few real problems that approach this sort of connectivity, and the problems we're going to look at in the future all involve graphs that are sparsely connected. So what we're really going to focus on is the adjacency list. We won't be using the matrix just because we're not going to have any graphs that really have that many edges. So let's discuss what an adjacency list is then, since it's what we're going to be using and it's what we're going to be implementing in the next lecture. An adjacency list is a more space-efficient way to implement a sparsely connected graph. In an adjacency list implementation, we keep a master list of all the vertices in the graph object, and then each vertex object in the graph maintains a list of the other vertices that it's connected to. In the next lecture, in our implementation of the vertex class, we're going to use a dictionary rather than a list, where the dictionary keys are the vertices and the values are the weights. So keep that in mind. Let's go ahead and show you an example of what this would actually look like. So for example, here we have our entire graph, and it has 6 vertices. So if we just look at one of them, right now we're just drawing this out as a list, but you can see that essentially each key of that vertex, V0, then has an ID, that V0, and it also has a set with the adjacent vertices to it, and the weights. So for example, V0 has ID V0, has adjacent vertices V1 and V5, with corresponding edge weights of 5 and 2. So you can see here we're actually not storing any empty data. So list is a much more space-efficient way than the matrix we previously saw. So again, that advantage of the adjacency list implementation, it allows us to compactly represent that sparse graph. And the adjacency list also allows us to easily find all the links that are directly connected to a particular vertex. So coming up in the next lecture, we're going to actually do an implementation of an adjacency list in Python. Okay, thanks everyone, and I'll see you at the next lecture.